All right, guys. So in the second part of chapter 4, we're going to look at a couple things all at once, right? So we're going to start with acids. We're going to look at oxidation numbers. We're going to look at gas forming reactions, and we're going to look at just a couple other, like titrations, a couple other things that are in this chapter. We will see all of these things in greater detail as the year goes on, but chapter 4 kind of introduces them to you, so that's what we're going to do. All right, so here we go. Acids, hopefully you remember from last year, there are Arrhenius acids and Bronsted-Lowry acids and Lewis acids, right? There are different categories or different ways, I guess, that we can categorize an acid. The initial definition by Savante Arrhenius was that acids are substances that increase the concentration of hydrogen cations in solutions. So when HCl goes into water, we would expect there, we would expect there to be HCl to dissociate into H plus and Cl minus. This is going to increase the concentration of hydrogen ions in solution, and so we would say HCl is an acid. Bronsted-Lowry kind of built on that definition a bit, and said that anything that donates a proton is going to be an acid, and thus anything that receives a proton will be a base. For the most part, acids are going to start with H. There is one notable example here. Acetic acid does not start with an H, but pretty much all the other acids do. Now, bases, which obviously if we're going to talk about acids, we've got to talk about bases. Arrhenius defines the base as anything that increases the concentration of OH in water. So that OH anion, so something like NaOH, when we put it into water, since sodium hydroxide is certainly an Arrhenius base, I would get Na plus and I would get OH minus out. This is increasing, right? I have more OH minus than before, and so that would be an Arrhenius base. Bronsted-Lowry, like we just said, well, they're actually proton acceptors, okay? So a good example of that would be ammonia. Ammonia can be like NH3 can become ammonium if it accepts a proton. So NH3 plus an H plus would give us NH4 plus. So in this case, whatever this acid species is, the spectator ion is pretty much irrelevant here. But the hydrogen is going on to the NH3. The NH3 is accepting it, and so we say that is a proton acceptor. Thus, in this case, NH3 is a Bronsted-Lowry base. Bases also turn litmus paper blue. Acids turn litmus paper red. That's something you probably already know, but it's worth a mention. Now, something that may be new, or not new, something that we're going to build on from last year, is the determination of whether or not acids are strong or weak. And we'll see this a lot more when we get to our unit on acids, but just so you know now, right, we just talked about those net ionic equations. We know disassociation in water is really important for ionic compounds. So something that we can kind of tag together there, a strong acid is going to completely dissociate in water. Weak acids only partially dissociate, okay? Strong bases are going to completely dissociate into their metal cation and their hydroxide anion. Weak bases, not really going to do that. They're just going to partially dissociate, okay? You guys want to know the strong acids and the strong bases. If you know the strong ones, the weak ones are everybody else. So like there's only 7 strong acids. Now, something to keep in mind, when I'm saying these acids are strong, that doesn't have anything to do with how corrosive the substance is. The strength, all right, of an acid, when we say strong here, is just referring to its ability to release hydrogen ions in solution. That's the only thing that makes an acid strong. Great example of this, okay? HF, hydrofluoric acid. HF is not on the strong acid list, but it is extremely corrosive. So it doesn't release its hydrogen ion very well, but that doesn't have anything to do with how corrosive it is as a substance, all right? The strong acids are HCl, HBr, and HI. So 3 monatomic acids, all with the halogens, not including fluorine. There's chloric acid, which is HClO3, perchloric acid, which is HClO4, nitric acid, and sulfuric acid is a strong acid. Now, sulfuric acid is a diprotic acid. We know it's diprotic because the acid has H2, right? There's 2 hydrogens on there. So sulfuric acid looks like this. It's a pretty cool Lewis diagram. And if you're in my class last year, we had a pretty cool talk about old sulfuric acid, which I'm sure all of you remember in great detail. So this is what sulfuric acid's Lewis diagram looks like. And the first proton that it gives off very easily. So we'll just say it's this one, all right? It gives that away, and you have, let's draw a little arrow there. We have HSO4 minus plus H plus. Now, the second proton, which is this fellow right there, all right, if we were to draw out its dissociation reaction, there would be a little bit of a difference. It would look like this. HSO4 minus, and then we would have equilibrium arrows to go H plus and SO4 minus 2. Now, here's a dead giveaway. If you see those equilibrium arrows right there, all right, that means you're talking about a weak acid or a weak base because it's not fully dissociating, right? It's at equilibrium. Some of it's dissociating, it's going that way, but some of it's being reattached, so it's not complete dissociation. On the other hand, if I look at the initial reaction, right, H2SO4, oh, forgot the S, there we go, completely dissociates, right? It's just a singular yield arrow into H plus and HSO4 minus. So we have a 2-step deprotonation here. The first step is a complete deprotonation. I can tell because the arrow is just one direction. The second step is an incomplete dissociation, and I can tell that because I have the equilibrium arrows, okay? So just something to look for. And again, we will do a lot more with that when we get to bases, okay, and acids later in the year. Hopefully from last year, you remember the acid-base neutralization reactions, all right? If you have a metal hydroxide, so something like NaOH or CaOH2, something like that, then you're going to get a salt, right? That ionic compound, water, that kind of thing. That's not always the case. Those are Arrhenius acid-base neutralization reactions. Remember, you know, as we get into AP, there are more than one kinds of bases. Well, there's also more than one kind of neutralization reaction. So the one that I've got here to show you is actually an acid-base reaction between water, which is amphoteric, so that means it can be an acid or a base, and ammonia, which in this case, this is making hydroxide and NH4+, ammonium, right? So my water molecule here is donating a proton. That's what's happening here. This proton right there, this H plus, is now right here, okay? And so it's still considered a neutralization reaction, but it's not going to give you that water and salt nice and clean like we thought always happened in year 1 chemistry. Now, the neutralization things that you are familiar with, though, like a strong acid with a strong base, in this case, this would be an Arrhenius acid, and this would be an Arrhenius base, right? AC, there we go. I'm going to get that nice, you know, production of a salt and water, right? So here is my ionic salt, and here is obviously water. And that's going to come from the Na and the Cl. There's my Na, and there's my Cl. It's a special type of double displacement reaction, okay? And the net ionic equation we have down here at the bottom. Let me find a place to put my face that's out of the way. There we go. So this would be our ionic equation, and this would be our net ionic equation, which this is pretty interesting. It just shows, hey, we're making water, right? Interesting stuff. Okay, so what I want you to be able to get from this. Number one, there's more than one kind of way that acids and bases can react. Last year you learned about this one, right? It makes salt and water. There are also reactions like where water reacts with ammonia, which may not necessarily give you a water and a salt, okay? If you have a reaction like this, you should be able to write the Ionic equation, right? Break everything apart into their species, use your solubility rules to add the aqueous at the bottom, aqueous, solid, liquid, whatever it is, and then we should be able to come up with a net Ionic equation by marking out our spectator ions. Remember, the things that don't change. We will do more on acids and bases in later chapters, so let's switch gears a little bit. Keep on going, chapter 4. There are gas-forming reactions, and we really don't talk a lot of detail about those in the first year of chemistry. So this is another metathesis reaction, and when you look at this, like immediately, let me put my pen over here so it works. Go back. There we go. So I have a metal and a non-metal. So I have an ionic species, right? A metal and a polyatomic ion acting as a non-metal. I have my metal and my non-metal, right? An acid, but it's still, a metal and a non-metal. So I would look at this and I would expect, hey, I should get a double displacement reaction here, right? So if we, covered up this and said, okay, you're not allowed to look at the answer, you look at over there on the left and you'd say, all right, well, this should be double displacement, right? So calcium should end up with chlorine and H should end up with CO3, and I'll, balance, I'll cross multiply, or not cross multiply, wow, I will cross my charges. And so I should get H, and we know CO3 is carbonate, and so, yada, 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 and I'll get like CaCl, and this would be 2, and yada, yada, yada. Okay, this would be 2. There we go. Well, that's not what we get, all right? Something to kind of point out, right? When you have a carbonate or a bicarbonate in a reaction, okay, so we're just building on what we already know, that's not going to follow the double displacement rules. That's going to be a little bit different. You're going to get salt, you're going to get carbon dioxide, and you're going to make water. So the salt is still going to form between the metal and the non-metal. But the carbonate and the hydrogen are going to form CO2 and water. So these two together are going to form that right there, okay? So something to add to our knowledge base, right? We have double displacement reactions, we have single displacement reactions, we also have gas-forming reactions. Gas-forming reactions look like double displacement, but we'll spot them because we'll see I have a carbonate or I have a bicarbonate. This is sodium bicarbonate right there, this baking soda. And again, I'm going to get CO2 and water, and my metal and my non-metal are going to make the salt. All right, wow, that was a terrible arrow. Okay, so those are our gas-forming reactions. We'll add that to our list. Here's another one. All right, this one stinks. It smells really terrible. H2S is an awful smelling gas, right? Hydrogen sulfide. I have Na2S. I have H2SO4. Now, you'll notice it's not a bicarbonate, okay? Just this is a sulfur compound and sulfuric acid. This is just a great example of chemistry not following all of its rules, right? But this would be an example of producing a gas. So when I look at this and I'm like, hey, why is this a gas? Well, look at your solubility rules. You'll notice that when sulfur is S-2, right, it's not going to dissolve. However, it's not going to be a solid here. It's going to be a gas. Okay. Let's switch gears again, right? Chapter 4 kind of hits some high points. So redox reactions. Now, last year we talked about redox reactions. Let's see, what did we do for redox? When we took the graduated cylinder, all right, I had to think there for a minute, took the graduated cylinder in first year chem, and we put that nice pretty blue liquid in it, that copper compound, copper sulfate, and then we stuck aluminum foil down in there, and it went from that nice pretty blue, and then the copper like rained out of the water, precipitated, and the aluminum foil got like eaten up and disappeared, and the water went kind of gray. That's a redox reaction, okay? It's also, in that case, a single displacement reaction. So when we talk about redox last year, you probably remember oil rig, all right, which is oxidation is loss, reduction is gain, okay? Another way you can remember it is, let's see if I can get my pen to work here. There we go. Leo says, grr. Leo the lion, right? Loss of electrons is oxidation. Gain of electrons is reduction. Two ways to remember it. I prefer oil rig, but if you like Leo the lion, so be it. You can't have one without the other. If something's being oxidized, something else has to be reduced. We usually call these redox reactions, right? As in this right here, redox, okay? And we'll look a little bit more of that, okay? So in order to do redox, you have to know how to assign oxidation numbers. Now, we did oxidation numbers last year, and oxidation numbers basically account for the charges inside neutral or charged molecules. So there are some rules for this, all right? Number one, in the elemental form, so a pure element, an atom has an oxidation number of 0. If you have a monatomic ion, the oxidation number is the same as its charge, right? So a monatomic ion would be like S minus 2. So what's the oxidation number? -2, all right? The monatomic ion has the same oxidation number as its charge. If I have something elemental, so let's say I just have sulfur by itself, well, then its oxidation number is 0. Nonmetals usually have negative oxidation numbers. Some of them are positive on occasion, like oxygen can be -1 in peroxide, but for the most part, it's safe to assume it's -2. Hydrogen's -1 when bonded to a metal, but it's +1 when bonded to a nonmetal. So for hydrogen, we want to look and see where it is. If I have HCl, well, hydrogen is out front. It's acting as the metal here, so it must be +1. Chlorine is going to be -1 because the overall oxidation state, has to equal 0 because this is a neutral element, a neutral compound. Fluorine is always going to be -1. The halogens are always going to be -1 when they're negative. They can be positive if they're in an oxyanion, so something like a chlorate or a perchlorate, something like that. But for the most part, they're -1. The sum of the oxidation numbers has to be 0 if the compound is 0. The sum of the oxidation numbers has to be the charge if you're talking about a polyatomic ion. So what do I mean by that? Well, let's look at SO4, 2 negative. All right. We know that oxygen is -2. I have 4 of them. So oxygen is a total oxidation state of -8, right? -2 is the oxidation state. I have 4 oxygen atoms. So that's a total charge of -8. Sulfur, -8, must equal -2 overall because that's the charge. So +8, +8. Sulfur in this case is +6. So we would say there is the oxidation number, +6. Now, whenever there's a displacement reaction, a lot of times the ions are oxidizing an element. So this is one that if we come back in school, I'll actually do with you guys. It's a pretty cool reaction. We're going to take silver nitrate and copper. We put the copper down in there, and the silver literally just precipitates out of solution. And you can kind of see what's going on if you look in this middle thing here. This electron, all right, is being stolen away from copper by the silver, and silver is being reduced. It's gaining those electrons. What this ultimately leads us to, right, is this product over here, which has pure elemental silver, which we can see right there kind of hanging on to the side, and this copper nitrate. Copper nitrate is this aqueous, nice blue solution that we're developing there. Now, common question, right? Why doesn't this recur in reverse? Okay, what prevents it from oxidizing the silver and then reoxidizing the copper? All right, why does that? Or sorry, reducing the silver and then reoxidizing the silver. Why doesn't it happen back and forth? Well, there's this thing. It's called the activity series. All right, you want to learn the activity series. The things closer to the top, all right, are more reactive. Reactivity is going to follow some of our trends, so that's useful. But this is something that you just kind of want to keep in your mind. So learn this table, write it down. You don't have to necessarily learn the reaction, just learn the table. The things near the top are more likely to exist as ions. So that's how I can tell if I have silver and I have copper. Where's copper at on this thing? Right there, right next to each other. Copper is more likely to exist as an ion than silver. So if I go back to this reaction, here copper is not an ion and silver is an ion. It's dissolved in solution and it has a charge. Well, the activity series says, nah, that's not very likely. It's more likely that the electron get donated over to silver so it's stable and that copper become the ion. Since copper is higher on the activity series, the reaction proceeds. Copper becomes oxidized. So I go back. Copper becomes oxidized right here. Silver becomes reduced, and I get silver, which is neutral, not an ion, and copper in the aqueous environment, right? So this is going to break apart, and I'm going to get Cu plus 2, and I'm going to get NO3, and there's 2 of them. But they're going to be broken apart, right? Because it's aqueous. It's dissolved in solution. So that follows the rules of the activity series. The activity series tells us, without ever doing any experiments, hey, if I mix these two things, will they react? Will something likely occur? For example, let's say I asked you, if I have, stable iron and I have zinc as an ion, will those two things react? Well, here's stable iron, here's zinc as an ion. So no, they would probably not react when I put them together because zinc's already an ion and that's what the activity series says it should be. On the other hand, if I said, look, I've got some sodium that's pretty stable, it's just regular old Na, and I've got some, we'll say zinc, which is +1. Are they going to react? Well, yeah, probably, right? Because sodium is more likely to be the ion because it's higher up on the activity series. So that's something that this is useful for. Now, we use it to talk about metal and acid displacement reactions. So a lot of times when you go back and you look at this chart right here, we can say, all right, well, here's hydrogen. So if hydrogen reacts with these as in the form of an acid with any of these metals above it, we would expect there to be a reaction. However, if you put acid on any of these, we would expect there probably not to be. All right. So when you put metals, those active metals, into acid, then we can oxidize them to a cation. Okay. All right, we're almost done. So molarity is something we talked about last year, kind of switching gears again. Molarity measures the amount of solute in the solution. We call that concentration. We order, the big M is the symbol that we use to talk about molarity. It's moles of solute over liters of solution. So another way that we write this is M equals moles divided by liters. Probably easy review there. When you mix a solution, okay, if you want to know, if you want like a 2 molar solution, all right, you're going to weigh out the mass in accordance to the number of moles that you need, okay? You're going to add that to a flask, and we're going to fill up the flask with the solvent, usually water, right? So this is something that we'll do in the lab when we come back, if we come back. When we dilute things, all right, we are taking a concentrated solution and we are kind of watering it down, right? So we can see, we can see down here we have a nice concentrated solution here on the right. We add a little bit of it to the left and we add water to it, and this dilutes it. The dilution equation, all right, is M1V1 equals M2V2, molarity times volume 1 equals molarity times volume 2. You can see that right here. And so C and D are the concentrated and dilute solutions. A lot of times we just use 1s and 2s. All right. If you want to use molarity in your stoichiometric calculations, which you likely will do, This little chart here will kind of walk you through how to convert some of those things, all right? So I know we did molarity last year. I'm not feeling like that's hard for you guys, but if you have questions, absolutely let me know. This is definitely worth a little review here. The last thing we're going to talk about today is the titration. All right, a titration is something we actually didn't get to do last year because in first year chemistry, as far as the lab, because we all got sent home about the time we were doing acids and bases. So a titration is a way that we can figure out the concentration of an acid or a base when we don't know it, using some knowns and using the titration equation. So in order to do this, all right, we're going to look at what's called a standard solution. That's the solution that we know the concentration. And we're going to try to get it to go to what's called the equivalence point. The equivalence point is where the amount of standard solution in our beaker is enough to neutralize all of the unknown solution in our beaker. They are at equivalence. We'll see more about that when we get to the acids and the bases slide, but that's just a brief review, okay? So for today, or sorry, for the remainder of this PowerPoint, let me jump down here so we can just see. All right, that's the end of chapter 4. Okay, let me know if you have questions. I know chapter 4 seems kind of to gloss over a lot of material, but that's it as far as the notes. All right, so let me know if you have questions, and I'll be glad to give you a hand.